Welcome to the Explainer. Today, we are cracking open the secrets of concrete. You know, the most used man-made material on Earth. But we're not just talking about your average sidewalk here. We're going deep into the hidden chemistry that lets us literally control its internal clock, telling it exactly when to set. So let's just start with the main puzzle, right? Concrete has its own mind. It's got an internal clock, and it wants to harden on its own schedule. But what happens when that schedule just doesn't work for us? You know, when it clashes with a tight construction deadline, or a really hot day, or maybe a long haul in a truck. How do you actually take control of that? Okay, so here's what we're going to cover. First, we'll look at concrete's internal clock, then the whole speed up versus slow down thing. We'll dive into the chemical mechanism, then this crazy idea called the Dosage Paradox. We'll even look at some air bubbles and anecdotes and wrap it all up with why this chemistry really matters. All right, let's dive in. So the number one problem here, it's all about time. See, for any big construction project, concrete has to stay liquid long enough for you to pour it and get it into shape. But then it's got to harden up fast to get strong and keep the whole project moving forward. It's this constant, tricky balancing act. So how do they do it? Well, the answer lies in these things called chemical admixtures. You can think of them as the secret ingredients, really, that engineers add to the mix. This is how they take direct control over how concrete behaves. It's what turns a simple mix into a truly high-performance material. Okay, so when we're talking about controlling time, you really only have two choices, right? You can either speed things up or you can slow things down. Let's meet the two main players that get this job done. It really just boils down to a simple choice. Are you hitting the gas or are you slamming on the brakes? Accelerators, well, they're the gas pedal. You'd use them when it's cold outside to really kickstart that hardening process, which means you can take off the wooden forms and stuff way earlier. And then you've got retarders. Those are the brakes. They are absolutely essential on a hot day when the concrete wants to set way too fast, or for those long trips in the truck where it just has to stay liquid for hours. Okay, but how does this stuff actually work? Like, what's happening down at the molecular level? It's not magic, I promise. It's actually this incredible chemical dance that makes all this control possible. All right, here's the absolute key to understanding this. The hardening of concrete, what we call hydration, it isn't just one big poof and it's hard. It all kicks off when the different chemical compounds inside the cement start dissolving in the water. And that is the secret. The speed of that dissolving process, that's the thing we can actually control. That's our in. So this chemist, Joyzel, he came up with a really brilliant way to think about this. Picture it like you're managing a team of ions. You've got these super fast-reacting ions called aluminates. And then you have the slower ones, the silicates. An accelerator, well, it's kind of like a coach for those slow silicates, yelling, hustle, speed them up. A retarder, though, does the opposite. It goes over to the super fast aluminates and says, hey, slow down, let the rest of the team catch up. The whole game is about keeping that reaction perfectly in sync. Okay, now, this is where the science gets really interesting. And, honestly, kind of weird. It's completely counterintuitive. You'd think, okay, I'll just add more of a chemical to get more of the effect I want, right? Well, with concrete, that's not always how it works.
Yeah, that's the paradox. You'd think adding more retarder just means it slows down more, but no, the relationship between the dose and the result is, well, it's complicated. It's not just about what you add, it's all about how much.
And this is where it just gets wild. Take a look at these type 2 and type 3 chemicals. At a low dose, they do exactly what you'd think a retarder does. They slow the reaction down. But if you add just a little too much and cross a certain threshold, they completely flip. They become powerful accelerators. I mean, think about that. The very same chemical can have the exact opposite effect depending on the dose. It's crazy.
Okay, let's make this super clear with a couple of real-world examples. Calcium chloride, everyone knows it as a powerful accelerator. But here's the catch. You have to use enough of it. If you use too little, you could actually end up slowing your mix down by accident. Now compare that to something like lignosulfonates. This one is your classic reliable retarder. With this stuff, the more you add, the slower it gets. No surprises. And this is why getting the dosage exactly right on a construction site is just absolutely critical.
So, this whole world of admixtures, it's about way more than just controlling the clock. These chemicals can also fundamentally change the actual structure of concrete to make it tougher, more durable. So let's look at another one of these crucial functions and check out some stories from the field. Now, these things, Air Entraining Agents, they are absolute lifesavers for any concrete that's going to see a cold winter. They're basically a special kind of soap that creates billions, literally billions, of tiny, stable air bubbles all through the mix. So, when the water inside the concrete freezes and expands, which it always does, these little bubbles act like tiny pressure relief valves. They give the ice a place to expand into, so it doesn't crack the concrete apart from the inside out. It's brilliant. But it's super important to understand that not all air in concrete is good air. There's a huge difference. You've got entrained air, that's the good stuff we just talked about. It's microscopic, perfectly round, and it's engineered in there for durability. And then you have entrapped air. That's the bad stuff. These are just big, ugly, irregular voids you get from not mixing properly, and all they do is kill the strength of your concrete. They're basically just defects. And the science behind this is so precise. For this whole system to work, the distance between any two of these tiny air bubbles can't be more than 200 microns. That's incredibly small. And the reason is, you want to make sure that as water starts to freeze, it doesn't have to travel very far to find one of those little escape pockets. That prevents this massive buildup of pressure that would otherwise it would just tear the concrete apart. This little story just perfectly shows the huge gap between the super precise chemistry in the lab and the, let's say, messy reality of a job site. So this pro from a chemical company tells the story about a truck driver who was adding 10 gallons of water to his mix for every hunk the concrete made inside the drum. He was judging the entire mix by sound. I mean, it's a perfect example of how this incredibly carefully designed chemical mix can be totally thrown out the window on site. And that's why understanding this science is so important for everyone in the chain. And the applications for this stuff are just mind-blowing when you think about it. You can use admixtures to stabilize the leftover wash water in concrete trucks so it can be reused, which is great for the environment. Or think about oil wells. They use a complex mix of these chemicals to pump cement slurry for miles down a drill hole and then have it harden up super fast. And that bulging drum, that's a real thing. It's a warning sign that bacteria have literally eaten the admixture and the product's no good anymore. Okay, so let's zoom out for a second and bring this all together. Why have we spent all this time talking about what might seem like a pretty niche bit of chemistry? What's the big picture? Why does any of this matter? Because here's the thing, it's not obscure at all. This invisible chemistry is happening literally all around us, in every modern structure we count on every single day. Think about it. From the skyscrapers where they have to pump concrete hundreds of feet straight up to those massive bridge foundations being poured in the middle of a heat wave. Being able to control concrete isn't just a neat trick. It's what makes our entire modern world possible. So, if you're going to remember anything from this, remember this. First, concrete is not just a static blob. It's a material we can fine-tune with incredible precision. Second, admixtures are the knobs and levers on our control panel. Third, and this is a big one, dosage is everything. It can literally flip a chemical's effect on its head. And finally, this hidden science is really the unsung hero of the built world around us. It's so much more than just a lump of rock and water. It's a high-performance material, one that's been carefully designed and fine-tuned with a sophisticated chemical cocktail to do its job perfectly. And that's our explainer. So we'll leave you with this to think about. What other invisible chemistry is out there, holding our world together? You know, just beneath the surface of all the things we take for granted, there is so much hidden science at work.